Hello and welcome. This is Active Inference ModelStream 16.1. It's December 6th, 2024. We're here with Eli Sennesh and Tommaso Salvatori discussing divide and conquer predictive coding. So thank you both for joining. Eli, to you for the presentation.
All right. Hi, everyone. So I recall being here once before, presenting that old paper, interoceptionist modeling allostasis as control. And I think at the time I even mentioned that there wasn't really an inference algorithm that I could just go and apply to all of these kinds of active inference and predictive coding problems. And over roughly the last year, let's say, we've started work, this little team of myself, Hao Wu, who is unfortunately not on the stream due to having a 9-to-5, and Tommaso Salvatori, who's here with us. We've actually been working on this. How would we take these theories and, this predictive coding idea and just turn it into a Bayesian inference algorithm you can use for stuff? So, as background, to really refresh ourselves, this is the super short, NeurIPS version of our talk. There's basically theoretical neuroscience, neuro AI, or now, I don't know, Tommaso, what keyword do you guys use it versus? I should have asked you maybe.
We do use neuro AI actually. Bioplausible deep learning. That's a sentence I often use.
Yeah, so
I think that dates back from even before my versus times, I guess.
Yeah, so the broad theory is that, predictive coding sort of solves two tasks for the brain, and that's credit assignment and Bayesian inference. Now, predictive coding is also a thing in machine learning now. They do a lot of it at Versus. Tommaso's done a bunch with it. But it doesn't always, for various reasons we can go into, it sometimes doesn't always scale as well as backprop, basically. And so we basically started over again, I guess you could say, with the concept of predictive coding to build our divide and conquer PC algorithm. And we basically find that you can use this at roughly the same scale you would with VAEs. So, of course, in order to, test it out, we had this deep latent Gaussian model. It's actually the same one from, I think, the Monte Carlo predictive coding paper out this year. We really did this a lot, leaning on, comparing to other predictive coding papers rather than to some arbitrary baseline, because we figured if we pitch this as being about bioplausibility, then we can sort of maybe actually get results that are good enough to publish. Anyway, yeah. So we racked up our first win there. We went and compared to other algorithms that were related or inspired us. So the trained really is actually interesting is, basically we would say, all right, you have, yeah. Oh, after, demonstrating that this quote unquote wins, okay, it works well enough. Oh, this entire slide, yes, okay. Yeah, so our DCPC, in addition to being a predictive coding algorithm, is a particle algorithm. So it's training a particle cloud, so to speak, to approximate the posterior distribution in a Bayesian inference problem. So as such, we compared it to this algorithm particle gradient descent, PGD, from which we were drawing pretty direct inspiration. And then we also compared it to, Langevin predictive coding out at ICML this year. And so we compared on, the pressured inception distance that people use in deep learning rather than on, the variational bound to the surprise. We didn't compare on log evidence because that's, you can often get very bad visual samples from a model that has a very good log evidence, actually. So in order to, sort of say like, okay, that, log evidence is not the only thing that counts, we, compared on this pressured inception distance. Over here, we've got some samples from our pseudo-posterior predictive distribution. So it's a proper predictive distribution, but constructed from a pseudo-posterior. Pseudo in the sense that like we're fitting, I think, a small Gaussian mixture model to our big particle cloud of the actual posterior distribution. And then having done that, we say, all right, now we'll draw samples from this GMM as a pseudo-posterior, then pass those latents through the generative model again to generate samples. And, the actual neural architecture here is basically a one-level VAE. Like you just chop off the encoder from a one-level VAE that would be used in these baseline papers, use the same neural architecture in PyTorch, and then basically just got, slightly better results visually by just improving the inference algorithm and the training. Okay, did you manage not to lose that? Cool. Okay, so sort of the interesting stuff about it, especially compared to previous work, is how this actually works. As I said, it's a particle algorithm, so we're actually drawing samples. I think I said before we went live, this is sort of the year of Monte Carlo predictive coding methods. We're one of maybe, 3 or 4 that are out this year. So after you've like initialized your graphical model by just doing, ancestor sampling to get yourself some initial, cloud, what you can do during, every inference pass is start from the bottom up. So that's, the right over here would be the quote unquote bottom of the hierarchy. You can calculate, your prediction errors, which are the same kind of thing as in previous predictive coding work. There's score functions with respect to the latent variable. And the thing that we actually do differently from other work is that rather than just taking like a score function as a local gradient let's say, rather than taking a score function as like a direct gradient of the variational free energy, we take score functions with respect to the log complete conditional distribution. So like a coordinate update distribution, if you have, this variable Z1, then its complete conditional is the distribution of this variable Z1 given its entire Markov blanket. So given both, the predictions coming in from above it and the observations coming in from below. So that's why rather than one, error unit we have an error unit that connects, Z1 to the observation below it. We also have an error unit that sort of recurrently tries to draw Z1 back towards its local prior until that prior is changed by an update at Z2. So if you think about, how Bayesian inference works, Bayesian inference is just what you get when you have one distribution and it has to be normalized, but you're trying to fit it as closely as you can to both the likelihood and the prior at the same time. And so when you try to do that locally within a big structured graphical model, the logical posterior to go after is the complete conditional. And that's what we actually did. And I want to shout out Hao here because he's not on the stream, but his previous work on amortized population Gibbs samplers is really what showed that this kind of sampling from the complete conditionals could work at scale and, inspired this project pretty directly. This is kind of follow-up work to, his paper on that. And the way that we, sort of make this work in terms of constructing a free energy, or in terms of making sure we target the correct joint distribution, is that we can use Langevin proposals. If you have a prediction error from E sub 0 and another, E down sub 1, add them together, you have the gradient of the log complete conditional. Now it's the log unnormalized complete conditional, but that's fine because, the gradient doesn't, when you take a gradient of a log density, the normalizing constant falls out. And so you can target that with, a Langevin dynamics proposal, which just says take your previous prediction, multiply your prediction error by a learning rate, add the prediction error to the previous prediction, and then add some Gaussian noise. You have to balance the magnitude of the Gaussian noise with the learning rate in a certain way, but that's a detail. Really, it's saying let's be in the latent space, then let's follow the gradient, and then let's inject a little bit of noise so we explore most of the time. Or rather, sorry, so we explore some of the time while exploiting whenever the gradient signal is strong enough. And then, I note that we use sequential Monte Carlo here, and what that's actually for is that sequential Monte Carlo algorithms give you a whole set of rules for how you can start from, the proposal that you sample from, then go to the local target that you are actually trying to, that you're trying to sample from, and then combine those in, a neat way to get samples from the complete joint distribution. So you would do this, start here from the data on the right, do this predictive coding step for Z1, be done with it, repeat the same predictive coding step for Z2, but now with a new prediction error from Z1 down here, repeat all the way up here, and then you have a bunch of samples from different complete conditionals, and you have to come up with some way to say, well, what's my free energy? Or in SMC terms, what's my importance weight? And that's really where, the SMC technique becomes helpful, is for proving the whole thing is correct. So if you think, we named it divide and conquer because, what we're essentially doing is we divide the graphical model into these complete conditional units. Then we conquer each of them with, basically a Monte Carlo predictive coding proposal. And then we conquer the whole thing by recombining them. So it really is like a divide and conquer algorithm in the classic sense. Also, the reviewers wanted us to name it something clearer than the old name. All right, so then, that's a summary of the talk, really, and then we can go into details of the paper and, anything else we want to talk about. But broadly, the idea here is that, predictive coding as a theory, enjoys biological plausibility for approximate Bayesian inference, which is, actually this really hard task. Like, in deep learning world, people use all of these awkward neural network arrangements to try and amortize inference. And then the people who are real purists are just doing Markov chain Monte Carlo because amortized inference isn't good enough for them. And to be fair, it's often not very good if you don't, structure your amortized posterior like just so. And more to the point, in neuroscience, like predictive coding theories have often been, built on like mean field assumptions about the approximate posterior. So then you just have a coordinate-wise representation of the approximate posterior. And it's pretty well known that like this can't actually get you a very close approximation to a correlated structured posterior. So that was where the trouble was. That was the problem that we took a first step on solving. And we got it to work well enough that you can substitute it for neural networks in some of these cases where people use neural networks. And we're going to be at the poster session next Friday at NeurIPS if anyone wants to come and talk to us. And of course, we have to mention the places that we work and our affiliations. All right.
Awesome. Thank you.
Thank you.
I'll stop the screen share.
Yeah, I'll ask some questions, and if anyone in the live chat has questions, they can write. Maybe just starting with the structured part. What do you mean that it's a structured problem?
Oh, yeah. So, like, this is the experiment, originally I looked at this and said, well, how do we actually replicate Howe's results from amortized population Gibbs? And that was like a full-on time series model in which there were, like some local variables that were updated at each time step, but also some global random variables that were standing, at the hierarchical level above. So, that was really like, I thought, okay, we need to tackle these kinds of structured problems. Because, go look at, I'm trying to think like, honestly, most of the time, most interesting generative models are going to be kind of structured. If there's more than one latent variable, and it's not just IID sampling, so any kind of hierarchical Bayes, time series structure, dynamical system structure, like all of this stuff that you find in cognitive science and neuroscience so commonly, and yet which is often, we've often sort of given up on doing anything better than particle filtering or amortized inference if you look in the machine learning world.
Okay, and the graphical structure you showed was a linear hierarchical model, or it was going from side to side. That's just graphical convention. So
Yeah.
Do you ever need to account for branching or
No.
any other kinds of structures? Or how do you divide and conquer when there's also splitting and merging?
So I mentioned about Markov blankets, right? As long as you're in a directed acyclic graphical model, then there's still a notion of a Markov blanket for every single random variable. That's the thing that you divide, the graphical model into, is variables with their Markov blankets. And, this is sort of intended to be a bit free energy principle.
Perhaps bringing the notebook up would help. I'll ask the two questions, so return to them as you see fit. The first is, how do you specify the model? what does it look like before training and what does get updated during training? And then the second question is, how do you take that step as a modeler between the structure of a given problem, like the handwriting digits, and adapting that to what? Is that something more generic, or does that graph need to already from some other source have structure that's amenable to the target?
So the target density that we would try to sample from is defined by the graphical model structure. And like that, yeah, that has to come from somewhere. So conventionally, if you're doing machine learning engineering, then that's sort of up to your choice as the user of our algorithm. It depends on what like domain knowledge you have about your application. And if we were talking about brains, then that structure of the generative model is something that evolved. And there could be, and I should mention, the recent versus work. Like, of course, you can also have, structure learning problems, throughout like development, but throughout development and through certain behavioral tasks. But like that gets you a bit beyond the realm of just graphical models. And so, we basically aimed at just a given graphical model. Take a graphical model as given and try to do inference in it. You can work your way up to the harder stuff later.
In practice, we often use deep neural networks because we try to replicate the experiments of other papers. So we had like multi-layers and the convolutional models.
Yeah, maybe share the notebook and or the repo.
Working on, yeah.
Yeah.
Oh, the GitHub repo is like, yeah, we can share that pretty easily. Yeah, I'm gonna put this first in the Zoom chat, then share my screen. Yeah, so in the GitHub repo, we attempt.
Just zoom in a little bit.
That's actually sure.
Yeah.
Yeah. So in the GitHub repo, minus a requirements file, we try to share enough that you could hypothetically download and run this like just from your command line. You would need, a Python environment that's got the necessary stuff installed, but all of that is standard stuff. So if you wanted to just rerun the MNIST experiment, you would literally run this command on your command line. And then you could also, start your tensor board and watch it train. Then we include like evaluation notebooks that, basically would help you to replicate the figures from the paper. And yeah, we actually have, yeah, we also share, some pre-trained like weights and particles. I know that's probably a bit of a colliding name with like weights and biases. In this case, the weights include the biases. Weights would mean neural network weights, and then particles would mean, the frozen samples from the posterior distribution for random variables. And then, of course, we just give, the table of results. And as a small bonus to everyone else who has to try and replicate our results, we include an implementation of the discretized Gaussian distribution. which is otherwise like buried in the diffusion models literature. Thank you very much. Yeah, and it's, under MIT license, so, you can pretty much go ahead and like fork this, contribute back. It's in the universal probabilistic programming language Pyro, since that's basically like the largest deep probabilistic programming language. Let's take a look at some of the notebooks. Let's see. That one's going to look like garbage. This one's going to look like not garbage. Yeah, so what this does is, it's basically like PyTorch and PyTorch Lightning. So you're going to like read some JSON file. And that's going to give you, your data, your model, and your trainer. Then, you're going to remind the trainer to just load the weights and particles from a checkpoint. The random variables are saved as part of the PyTorch Lightning checkpoints. Yeah. It loads them, blah, 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 blah.
Right there, when it says 357,000 trainable parameters, what is that number coming from?
That is the number of neural network weight. Like, that is the number of float 64s in the neural network weights. So that's actually a relatively small number because this was sort of a toy problem. And normally it would be more in the millions.
And where were those combinatorics specified?
Right here in the architecture specification.
That's after it, though.
Yeah, because you have to load the thing to print the thing.
Okay, that's just printing it out. But you specified it elsewhere what the structure would actually be, loaded it in, printed it out. Okay.
Yeah, the JSON file, tells you like which modules in the Python code that you have to load and all of that. So if we go look at, what is the actual training file that we were loading here, it tells you, load this model module, pass it these hyperparams, checkpoint this often, load this data set with like this hyperparameter and batch size. Here's like learning rates and the number of particles, the number of sweeps, meaning like passes over the graphical model, that you do per training step. Yeah, this is like relatively standard deep learning type stuff. Yeah, and when we've loaded the architecture, we actually print it out. So it's a simple like isotropic Gaussian prior. And then we're running it through, a linear layer, an activation function, a deconvolution layer, some batch, each layer includes batch normalization, two more convolutional layers with their batch normalization and nonlinearity, two more convolutional layers again, and then finally a deconvolutional layer that gives you the correct image size and channel number. Well, that's rude. Anyway, yeah, so then we have this method we call load particles, which just tells you that's really for loading the particles into GPU memory once you know which data items you're testing on. Again, like relatively standard, deep learning stuff, then here we say we're going to open a Python context handler by, clamping the graphical model to the pre-trained particles that we loaded from disk. So, if you load your posterior particle cloud from disk, then you have to say to the graphical model, I'm testing right now, don't do any additional inference steps, just use these samples, as your distribution. So then we run, we average over particles to get our reconstructions of, training images. Now we're going to plot them. Here's the actual reconstructions. So like they're, kind of blurry like you expect from a VAE, but it shows that, things did actually work. Then you say, okay, I don't want to look at reconstructions of training images. I want to know, do I have a trained generative model? So you clear all that stuff out, and you're going to get all of the training and validation, particles from disk for training your, for fitting your pseudo posterior. And you're going to predict some new images, using the pseudo posterior. Then, lo and behold, you plot out the samples from the pseudo posterior. They're kind of blurry, and they're not as varied as you would sort of like them to be. But that is what happens when you have a very simple generative model. Like, if you go back to this neural architecture here, this is nothing like a state-of-the-art, diffusion model or whatever that you would use for image generation. It's really just a bunch of neural layers stuck together, mapping a latent variable to an observation. Yeah. And then we're going to, having generated those, we go through, we calculate, some metrics across the validation data under a series of different random seeds. We can also sample from the prior rather than the pseudo posterior. And that gives us lower visual quality, but more variation, more realistic variation. And then, we calculate the statistics that we reported in the paper. Plus some statistics we don't report in the paper now that I think of it. Like the effective sample size. That one's a good one for inference nerds. You divide that by the number of particles you're using, and it gives you a sort of percentage that tells you, how well are you actually fitting the true posterior distribution with this batch of samples. And in our case, the answer is, yeah, about 92% effective samples.
Thanks. Maybe could we walk through a similar logic for the MNIST handwriting?
Yeah, totally. Let's see.
But I think it would be almost equivalent. It's just that we use a different model.
Yeah, it's pretty much the same, but you'll notice there's quote unquote 3 decoders here. So each of these is actually performing, a random Gaussian sampling step in between. So this is a proper hierarchical Bayesian problem. So you have a prior, then you have a forward conditional and a forward conditional. So you have 3 levels of latent variables. And then finally you have your likelihood.
What leads you to use those here? Like, do you sweep or scan over 2, 3, 4 layers? Do you explore out features equals other multipliers? Or what led you to this specification for the Lightning DCPC?
So in this case, we took this exact specification from Monte Carlo Predictive Coding, which is over here. So like we wanted to compare inference algorithms head to head. So we picked exactly the same generative model structure and, replicated it.
Awesome. Yeah, that makes a lot of sense, and it helps with the continuity and isolating the inference algorithmic component. Is there in a methods or a procedural step anywhere other than these, or are all that are needed these JSON configs and the notebooks like this?
So this is runnable. Like this should be runnable if you actually just download it and, if you download it and follow the links to download, the pre-trained weights, put them in the path that the notebook expects here, then you should just be able to run this. It should be point and click. I say should because, I've tried it, but I've tried it once.
Cool. Definitely opportunities for people to explore. And then what about the training step?
So that would be done from the command line as the repo readme tells us. That's this step.
And you watch on TensorBoard and make a manual call based on diagnostics, or how else do you determine?
I mean, I would generally say let it run, at least for these experiments, let it run to completion. Like, I know that if I'm stopping something partway in because of the diagnostics I see on TensorFlow, like for instance, a very noisy, staticky, like loss curve, well, that's how I know when it's not working. The experiments that are mentioned in the paper are actually, known to work. Like you can just leave that running until it's done and you will get, subject to differences in your random number generator, more or less the result we got in the paper. I actually want to say, like, this is one of the nice things about the sort of the culture of machine learning these days, is that everything is really expected to be not just replicable, but like idiot-proof replicable. As in, if you cannot just run this by rote and get the same result, then reviewers don't believe the result is real. Which is, very much for like replicability of science, the way it actually should be.
So we looked at faces and digits. Let's say somebody were looking at another kind of image classification problem. Cats and dogs. So what would need to be adapted? What kind of data would be in for the training step? And then to what extent do these same Lightning DCPC specs, structures work, or to what extent do the first or the secondary layers need to be adapted to alternative cases?
Mm-hmm. So this thing that gets called a graph inside the Lightning DCPC, you'd have to write a new one of these classes for a new problem. So let's say, for instance, that you want to do semi-supervised, Bayesian learning. My old advisor from my PhD had a paper about that. So if you're doing, say, cats or dogs, then you're going to want to specify, a new graphical structure that's rooted in a prior over your latent embedding. And then it should have, a pair of likelihoods, essentially, one being to the class label, which is going to be, it's semi-supervised. So let's say you only get class labels on about half the samples. And the other is going to be, for the actual image, which is going to be fully observed. And then after writing, what is it, a PyTorch Lightning data module for your data set, which tells you, it handles figuring out which data points are supervised versus unsupervised, because it's a semi-supervised problem. And then, you would put that together and run it more or less, you would write another little JSON file and just run it. And hopefully you would get, if your, architecture for the generative model is rich enough, then your latent embedding space should begin to capture, differences between the supervised classes and and give you good prediction on classification. And then if you wanted to do classification style testing or evaluation, you would present a whole new image as the observation, and then just perform joint Bayesian inference on both the latent embedding and the class label. And then check that your class labels are good, so to speak. For an unobserved class label, you're not getting a one-hot vector, you're getting, a series of logits or an element on the simplex that specifies probabilities of class membership. So hence my saying good rather than absolutely correct. You never get a completely absolute yes-no answer out of a classifier. At test time, at least.
I think in general, you could also generalize it to different kinds of data types. So it does not have to be, for example, continuous data as images. You could generate discrete distribution, or you can also generate time series distribution. This is something that has not been tested in this paper, but in theory, the theoretical framework would allow to do so.
Yeah, we have an appendix in the paper that extends the math to discrete distributions. That does take a mathematical extension, and then that, would take some more coding. So we don't, make any promises there.
So in past streams and journeys, Eli, as you mentioned, we discussed with Dean and others the anticipatory allostasis, and then Tommaso, we discussed the causal modeling. So where would you triangulate this work, or how do you see it as sort of drawing on or complementing or not? But it's just interesting that it's not a homeostatic model. Often in the organismal ethological active inference, there's a lot of focus on organismal behavior and these kinds of topics, homeostasis, allostasis being critical there. And then in the Bayesian modeling space, often there's a focus on the interpretability of smaller models and carving nature at the joints and all of that, not this more machine learning sort of specify it in a sequence of convolutional layers. So how do you see just having worked on those different areas, how do each of you see, because clearly this is a relevant contribution and advance. So in what direction, or how do you relate it with those prior pieces?
I think it depends in which direction you want to push this work a little bit forward. So, for example, if we're looking at the machine learning side, and we want to scale it up to larger models, larger convolutional networks, you don't get interpretability because of this method. I think the same interpretability you would have with a with the old algorithms, you have them with this one. What you gain apparently, what this work shows is that you get better performance. But then, of course, if you apply to, for example, directed graphical models or Bayesian networks that have a specific causal structure that you can observe, in that case, you're able to stay. You can do, for example, the intervention kind queries that I presented here like a year ago or something like that. And but I think that's not in the algorithm; is more in the kind of model you pick up. It's the kind of task that you want to solve, and whether you care about it or not. So let's say maybe for generating faces, for now we did not care about having an interpretable model.
What would you say? Yeah,
my
Eli.
answer would, I would sort of compare it to something like a car engine. You know, you need to design a car engine of a certain size and power in order to put in a certain, like weight class of vehicle. But that doesn't actually determine, whether that vehicle is a Honda or a Jaguar. If it's the same size and, weight class, then you can actually use a very similar engine inside both of them. And I think that's sort of, on the one hand, both the beauty and the pain in the ass of working with Bayesian methods is that, the promise on the sticker is that here's Bayesian methods and you're going to solve a very broad range of problems by reducing them to the same problem, which is Bayesian inference. And that's, sort of what the free energy principle is all about, is saying it's all really just reducible to variational inference, right? But now what you do find, if you go look at like PyMDP or a lot of, free energy type papers, is that they'll design a model for the paper in order to model some piece of interesting organismic behavior, but they'll include some real restrictions on the expressivity of that model, which is that it has to be solvable by something like, say, variational message passing. So then there's the question of, well, how do you stop restricting the model class according to what inference algorithm you're going to use? And that was really like the dirty secret of Bayesian methods that I learned in grad school, was you're always restricting the model class to what you have a good inference algorithm for. Or at absolutely last resort, running something like plain old Metropolis Hastings with a Gaussian random walk proposal and just waiting for like 3 weeks of compute and hoping. So, what we actually want to do here is to say, we have a better engine. Like literally, we have a better inference engine. You don't have to, now structure an entire neural network architecture of inference proposals. You don't have to play graduate student descent with your inference algorithm too much. Let's, assuming that, brains have some kind of wondrous generic inference algorithm that solves so many different Bayesian problems all at once, let's try to model that and then just use it, because it'll be more powerful and more efficient than, customizing to the particular generative model you want. And, really it's like first baby steps, but it is encouraging that, I think we show in the table, yes, like we trained a variational autoencoder, as a baseline to say, well, what if you're doing variational inference by actually, training a neural network to do it for you? And it's encouraging to show that we can do a little bit better with like a generic inference algorithm that doesn't need a separate neural architecture, compared to like build a second neural network and train it jointly with the first one.
I think something that is also exciting about this, I mean, at least for me, is that we've been working a lot with predictive coding algorithms for machine learning And I guess you can clearly separate them in like supervised learning and unsupervised learning. And in supervised learning, for example, you train like large convolutional models on CIFAR10, CIFAR100, or tiny ImageNet. It seems that we've kind of like hit a momentary wall. So it's up to a certain point, it's becoming really hard to scale up those algorithms. And I think like the whole community, and it's not only predictive coding. Like when I talk with, for example, the equilibrium propagation people, with all the like bioplausible deep learning community, there's a kind of similar problem that is when the model is more than 7-8 layers deep, it doesn't perform well. And for example, scaling it up to ImageNet is a pain. So a lot of people are taking a step back and say, okay, let's do a little bit more research to find out why and generalize and try to improve the performance. When using, for example, predictive coding for generative AI, so to generate images to sample data points in an unsupervised way, the first problem that we had is that like in machine learning, we had a couple of, until like 2 years ago, it was mostly a deterministic algorithm. So we were taking mostly Rao and Ballard's version, which was the classification one. There was no stochasticity. So a bunch of people, including me, started publishing like associative memory papers. It's like I give it a data set, and I can, by giving it a little bit of information, you can regenerate exactly the same data points. And then in the last year and a half, as Eli said, some people started developing sampling algorithms. And and basically the papers before ours a little bit, either they do it on MNIST and fashion MNIST, or they do it on like colored images like CIFAR10, CIFAR100, but they use some kind of gradient descent, so it's not a completely local message passing algorithm. And what we did in our paper is that we have a local message passing algorithm, and we compare against theirs by using basically exactly the same architectures, exactly the same number of epochs. I think in some cases even exactly the same learning rate and things like that.
As a small correction, we aren't actually a message passing algorithm.
Yeah,
we're not technically any form of sum product message passing.
No, that's a local algorithm, let's say.
Yes.
Local algorithm, yes. And we do well. Like for example, the images of faces you've seen may not seem perfect, but they are, at least from my perspective, better than expected. And the thing is, I don't feel like we have reached a wall in terms of performance. Like we've tested only on the architectures that other people have used before, and we do well. And for now, there's little knowledge on how much this can scale up. Maybe you scale it up like 2 layers more and doesn't work anymore. That's something that we don't know yet. But potentially it would be interesting to, for example, something I was messaging with Eli earlier this week is, can we scale it up to larger decoder-only transformer models, for example? Not like, of course, LLMs or things like that, but for example, something that is like a 4, 5, 6 layers deep transformer model. That would already be quite an interesting result. Definitely not an easy one, but I think there is definitely room to improve what's in the results of this paper.
Could you also maybe highlight how do you see local update rules as superset, subset, what have you, of message passing? What differentiates the locality of connectivity from something that you would explicitly, Eli, call a message as passed?
That's an interesting question. I guess I think for message passing, you could call like all the belief propagation algorithms, or at least basically some kind of this class of algorithms where you clearly state which information has to be passed from basically one latent variable to the other. While local message passing, and those kind of algorithms, they're all local. So it's since you define them to be this way, they must have local information. Well, probably if you generalize to local message passing in generals, there are some proposals, maybe including this one, in which maybe things are not supposed to be local. Like maybe you can, like, since it's a structured learning algorithm, you may in theory, get information from latent variables that are more far away. But then when you actually do the computation, they are local. But that's an answer I'm giving now to the spot. Maybe Eli has a better thought on this.
So I would say that message passing algorithms differ from ours in both their means and their goals. And really, it's the goals, actually, that they're starting from. So that family of algorithms, when people were working on it maybe, 20 years ago, what they were really trying to do was to get a summary of a posterior marginal distribution. So they just wanted to be able to pick out one latent variable for an inference query or a decision they needed to make. Say, what is the posterior on this variable given the data, not given any settings for all the other latent variables? And that sort of restricts, the space of tasks that you can really address with message passing. And it also, does end up meaning that, what you're basically doing is some form of sum product or really integral product, algorithm. And that gets you all the way out to, I think, probabilistic circuits are the most current and advanced form of sum product based, like exact inference algorithm. And they only support tree shaped, generative models rather than those that are, directed acyclic graphs in general. So trees rather than forests. And we said, well, let's try targeting, the full joint distribution of all the latent variables together. Partly because that's the most general form of a Bayesian inference problem, and partially because, if you have something like a hierarchical time series model from the active inference literature, you might need several levels of the hierarchy. You might need the latent variables across those levels in order to make, an action decision. Several levels of hierarchy might actually parameterize your policy or the thing that defines the inference problem you care about solving, as a modeler.
That's very interesting. Again, to the sort of settings that a lot of active inference literature has tackled. In these cases, it's like digit in, pixel intensities, etc., digit classification, generativity of digits out. How would it be similar or different with something like digit pixels in, T-maze behavior out, or robot arm out? Are you leveraging this identity or at least structural congruence with the recognition and the generativity? Or like a VAE, can you have something different coming in and have the output be something that's categorically different than the type that was used as input? Like action.
So I think one of the advantages of defining anything as a Bayesian inference problem is that it really changes your conception of what's an input versus an output variable. For a Bayesian inference problem, you start with a graphical model, you clamp several variables to be observed data. Those observed data are now your inputs. Your output is any aspect of the posterior distribution that you care to examine. So we don't have to be outputting, classification logits. We could also be outputting, we could be outputting, actions. You could have, say, an active inference time series module where your agent sort of gets some data at every step of computation, performs a full sweep over the entire, history of latent variables, and then and only then actually, makes a decision about what action it's going to take.
Which really highlights the importance of being able to specify the full joint distribution and then clamp down with nuance on what you want to be taking as observable, but kind of clamping down from a full joint and then just specifying and then having an inference algorithm that will facilitate that locally operationally, rather than trying to, amidst the constraints of which inference procedures you can perform, work within subclasses of graphical models that abide by those constraints.
Mm-hmm.
It's almost like it's a far cry in some ways from 2022 textbook, figure 4.3, the kind of POMDPs and the matrix multiplication that it gets implemented in PyMDP, the sorts of pedagogical cases that do highlight certain key moves. This, though, looks and feels so much more like a machine learning work, and it's really interesting though what this enables.
I think you also shape the work with respect to the venue you want to submit to.
Yes, I was just going to say, now that I found
when we were discussing which experiments to run, the first question is, are we going to submit a new RIPS? Yes. And it's going to be okay. Then it's going to be mostly image generation and and also a little bit the venue and a little bit what did prior work do. They did the image generation.
We picked out image generation because predictive coding networks had not yet been used to get this quality of result on unconditional image generation.
So what, other than the conference next week, what ways might you be taking it?
I think maybe probably there are many future directions. I guess from the perspective that interests me the most, I would be really curious about doing what I mentioned earlier about scaling it up. So, for example, how much can we push this kind of algorithm? So I think at some point, if we're going to have enough compute and maybe a faster, it is like some fast training, but probably like if it's implemented in a parallelizable library or things like that, you can run larger models, you can run a huge number of hyperparameter search, and you can see at some point where it scales up. Because it's also true, like we didn't do. I mean, there is we didn't do a huge hyperparameter search at the end. Like we did some, but it's not, but like definitely not comparable to what's standard in a machine learning paper in which they try like thousands of combination of hyperparameters.
No, we did not do grid sweeps of like hyperparameters.
Yeah, exactly. So I think there's room for pushing these for sure a little bit more, and hopefully much more. But this is I think scalability is something that is really hard to intuitively predict. Like Weiss models work well on 7 layers, and then on 10 they collapse. You just do it and notice that, and then I guess you can do some interpretability afterwards and understand the reason. But doing it before is always a tricky thing. And so I guess trying it is probably if you have a method that allows you to try fast and fail fast is the best way of scaling it up, I guess.
Yeah, so I would also say, based on some of the not so publishable results that I've seen in, for instance, trying to replicate Howe's work with like bouncing MNIST digits, how well this works often does seem to depend on exactly how much structure the generative model provides you, to give like prediction errors that point in the right direction rather than, well, in exactly the right direction rather than just vaguely the right direction. Right? So, what is sort of how smooth versus how tightly peaked is the landscape of is your free energy landscape? And when it's more tightly peaked, this algorithm seems to work, significantly better. Versus when it's not so tightly peaked, it'll often sort of get into the region of valid solutions and then get very noisy as it becomes like unable to decide which of the potentially valid solutions is really the best one to converge on. I would say it's not so good yet at dealing with like multimodal posterior distributions once a good generative model has been learned. So they're scaling it up to that. I'm also interested to see like how far could we take this on a fairly standard machine learning problem by just saying, every time we have more layers than would be biologically plausible to differentiate, just insert a random variable. Like parameterize a Gaussian right there, and then just say, okay, now, the amount of gradient calculation you have to do between layers is biologically plausible, and we'll use the predictive coding math to actually, effectively solve we'll have the random variables substitute for backpropagation in a certain way.
What do you mean by that?
So if you have like a 12 layer, I think Tommaso, you said like a 12 layer
So
energy based transformer or something.
So I think the general concept about biological plausibility is that you have a latent variable, another latent variable, and you want basically computing the gradients of the parameters to depend on both latent variables and not on other stuff that are in between. So, for example, if you consider the function that goes from one latent variable to the first, from the first to the second, to be a 3-layer network, the gradients of the weights of the intermediate layer or of the first, they would depend on the last latent variable. And this would basically make you break the locality assumption and biological plausibility. While if you consider like the function to be a single feed-forward or convolutional layers, it means that for every weight, you have a latent variable before it. So you have a presynaptic neuron and a postsynaptic neuron actually in practice. And this will basically allow you to, once you compute the gradients of the free energy, to have everything that depends on presynaptic and postsynaptic neurons. So this is the concept with biological plausibility. The problem that, for example, I'm noticing in when you do classification is that doing this allows you to propagate the error a little bit less regularly than backprop does, because backprop is sequential, so it shines a little bit for very deep models, especially if you have the right activation function. So I guess that's what Eli was mentioning when he was saying about.
Yeah. So if you have, for instance, 12, if you have, for instance, image, 12 layers, classification, right? Then roughly speaking, getting a gradient for the activations of the middle layer of the neural network depends on all the way on the final observation. Now, what we'd like to say is, well, how much ultimately, it's been proved that predictive coding in the limit implements backprop just very slowly. But what we'd kind of like to do is to calculate gradients a bit more quickly. And so what I was saying is that, what you could do is sort of take the middle layer and just say, well, this is going to be a random variable now. Like instead of, a single deterministic activation that has to be exactly right in order to pass gradients through, this is now going to be a Gaussian distribution over activations. And having done that, you can then use, our predictive coding algorithm to say, I'll try and, propagate through the latent space of possible, weights. Or actually, no, sorry. I'll try to propagate through the latent space of like layer activations, find, a relatively good solution, or rather a, particle cloud of relatively good solutions for those, and then update the weights in order to make, those activations more likely without depending on the final classification. So without depending on the entire like backwards computation tape of backprop. But at the cost of being a little bit random, let's say.
What's wrong with that?
Well, nothing, say, probabilistic machine learners and, say, free energy principle people and, active inference people. But, currently the machine learning world doesn't like it very much. They say Bayes doesn't scale. We're going to teach them they're wrong about that.
Well, it's super cool. If you have any other things you want to add, otherwise, good luck with the conference and with proceeding. It's super exciting, and I hope people watching this go to the repo, continue on some of the explorations that you've mentioned, and explore it in their own ways too.
Yeah, I mean, feel free to send questions to our email addresses that are listed on the paper if you are not able to get the repo to work.
Or if you make the repo work and you have ideas for follow-ups.
Yes, that too.
As well.
Yeah, we've got a few ideas already. Like, I think I was talking to Tommaso and saying, like, I've been meaning to write some code that will allow you to sort of pass a deterministic output between random variables so that we would, not just be able to do like graphical models, but proper stochastic computation graphs.
Divide and contribute.
Exactly.
Yes.
Cool. Thank you, fellas. Till next time.
Thank you very much, Daniel, for organizing this.
Yeah, thanks for running these. Like every time a new one comes out, it goes on my watch later list, which admittedly I never work through, but they do go on it. And sometimes one or two videos.
Cool.
When I get the opportunity to binge, you are what I'm binging.
Thank you. See you guys. Bye.
Have a nice day. Bye-bye.